Okay, I've just aligned with Professor Huang, and he'll be in charge of preparing exam questions. So we're going to cover, starting from MOS devices. So it's from chapter 6 to chapter 11, except I believe chapter 9, which talks about OP circuits. And one of the key things probably is very important to you is that the questions will be limited to MOS device and circuits. Okay, so you can leave bipolar out, even though I'm going to still talk about it a little bit as a reference. But we're talking about maybe in the future this class will be focusing more on MOS devices. This is mainly because of technology, because nowadays if you do any circuit designs, and it will be mostly MOSFET-based design, except for high-powered or high-frequency circuits. Okay? So just to tell you a story, when I was taking courses in design, if you know that a very famous analog circuit design book, I don't know if you know this book, textbook, it's called by Gray and Meyer, Paul Gray and Meyer. I was taking Professor Meyer's course in Berkeley, and then his course is mainly focused on bipolar circuits, because during that time, I think in the 1990s, most of the analog circuits are based on bipolar technology, because, as I said, bipolar circuits is very, let's say, high driving device, and that was the main device for analog circuit design. So most of your analog circuit design was focusing on bipolar circuits. And nowadays, because everything is digitalized, so you want to pair with this digital circuits. So when I was in Berkeley, one of my I should say friend, he was a Paul Gray student, and his research is on using CMOS circuit to realize certain analog circuits. So that was a research, because it hasn't been popularized or customized around. But nowadays, you don't actually see any. Most of the circuit, I should say, even the analog circuits, if you're making it in combination with digital circuits, the best solution is still CMOS technology. So this is just the trend of technology. That is why, even though we still want to keep some bipolar discussion in this class, but I think if you're taking more advanced courses, the focus will still be CMOS technology-based analog designs, okay? So because of that, let's review our MOSFETs, okay? So this will be in your exam because it will be focused on MOSFETs. So let's look at MOSFET models again. So I didn't actually go into details, but now I would like to sort of review this high-frequency model, parasitic capacitance models in MOSFETs. So if you want to look at parasitic capacitance in MOS, I want to highlight this is still based on what we call a planar device. Nowadays, you will see, we're probably going to talk about that in a little bit. If you take courses like solid-state devices, you will know that transistors start with planar structure. This is called a planar structure because all of your transistors are planarized. Your channels are plane. It's a 2D channel. So if we look at this, let me draw the cross-section. This is called the cross-section of a transistor. Typically, if you cut into a transistor's, called a planar. Of course, against planar, there's 3D transistors. Nowadays, you might have heard of technology like FinFET or nanosheets. Those are 3D transistors. So we're going to talk about more conventional planar transistors. So this is the gate. And as I said, for CMOS process, you would then build a well. This is called a P-well in a substrate, whatever substrate that is. Can be a P-sub. And then you have contacts to these terminals. So I would then have a P plus. This is for contacting metal contact. I have contacts, contacts, and contacts. So for a MOSFET, you have basically 4 contacts: gate, source, and drain, and body, to make the cross-section of your transistor. And we talked about the parasitic capacitance. As we already know, this is the main feature. I didn't actually do a good, let me do a better drawing on this gate. As we have already discussed, typically what happens is that you make your gate, the gate and the source and drain will then have some overlap region. This is the This is the gate dielectric with a thickness of Tx. And if you actually look into the cross-section, what happens is that there will be a lateral diffusion into here. So if I want to define the gate, this is the actual gate length defined by your gate. It can be a metal gate or a polysilicon gate. So this is the actual gate length, right? And there's this overlap region, this L diffusion, lateral diffusion region. And there's the actual channel called the L effective, meaning that is the real L, if you define it in this way. Okay? And once we have these geometry defined, the other thing is, of course, your capacitance. There's also junction capacitance at either source. Remember, these are CJ. These are junction capacitance called D to B. This is source to body. So both of them are junction capacitance depending on your source and drain area. So this is to look at your cross-sectional view. Of course, if you want to find out the real capacitance, if you ever did SPICE simulation nowadays, there is something called post-layout simulation. If you do called a pre-sim simulation, meaning that you don't actually have the layout, then it's very hard to extract these parasitic capacitance because it would depend on the size of your transistors or size of your layout. So to correspond to a layout to get more precise simulation results, typically what we need is, in additional to these are called the process parameters, junction capacitance, L and diffusion length, those are process parameters. And you also need layout parameters. So if you look at the top view, this is cross-section. Let me get rid of the piece. This is the cross-section. And if you want to look at the layout, meaning the top view, how you draw, then, as I said, there's parameters like this. So I typically have a active area and then define the gate. Like that. You could have, it's probably not too much information. Let me just leave it a simple way. Let's leave the body contact out in this case. Just look at the transistor itself. So this would then be your gate, and then the dimension here correspond to, this would then correspond to L. This would then correspond to W. Okay? And then what else? Let me highlight this. And you will then have contacts. These are contacts to make your, for example, source, drain. And then typically you would then have a shape like this, just to make sure that your contacts are landing right on the area. So this will be your gate contact. We're just going to leave the body out for this dimension. So aside from these two, there's another dimension. This is the width. Let's say the width or length of source. Let's define the length of drain. So once I have all these parameters, I could then determine the final model, extract all the models, the high frequency model parameters. So the high frequency MOSFET model then can be determined by, let me first draw the model. I have the original, without the parasitic capacitance, there's only two elements. One is transconductance, which is the drivability, to describe the drivability of the transistor. I have source, drain, and gate. I have three terminals. Okay? It's RO, GM, VGS. So that's our original small signal model. We want to add our parasitic. So the parasitic here is there's VGS, CGS, there's CGD, and there's source. To be more complete, if you look at your source to body, there's additional capacitance source to body. So if this is my body. And for drain, this will be D to B. And we know that in most cases, your body is connected to the most negative voltage or ground. So this is default ground. Okay? So you have these two more capacitance. Let's write down how we extract these parameters, or what are the dependency on, what are the things that determine these parasitic capacitance. As we already mentioned, let me write it down. I have C, among these capacitance, the largest one is, there's 4 capacitance. So first of all, you need to determine which one has the highest capacitance. We know that for parallel plate capacitance or diffusion capacitance, for that say, you view capacitance as parallel plate capacitance, meaning that as the distance between the charge reduces, meaning that if the distance between two electrodes determine unit area capacitance. So if it's closer together, meaning that it has a unit area largest capacitance. In the whole system, the largest capacitance in the system is actually being defined by this. TOX is in the range of, nowadays, start with 100 nanometer, maybe for 0.5 technology, all the way down to nowadays, this 100 instrument. So down to maybe 1 nanometer for advanced technology. So this is very, very thin, meaning that it has the unit. If you think about it, if the distance between two plates is the shortest, that means that it has the highest capacitance, unit area capacitance. That means that actually makes COX probably in the range, if you use this as a corresponding result, 3.45 femtofarad per micron square. If you look at this, this is actually a very high capacitance in the system. If you ever do junction capacitance, typically in the range of maybe 0.1. So this type for junction capacitance is probably 0.1 or less than 0.1 femtofarad per micron square. It's just to give you an order of magnitude difference between the two, because junction capacitance depends on depletion width, and the more depletion there is, or lighter doping, it will then make this depletion much wider than this, so that you have a unit area much smaller capacitance. So once you have this number, it gives you a sense as to, let me just highlight, this referred to 100 angstrom as 10 nanometers thick. Okay? So once you have this number, you sort of get a sense as to, if I want to evaluate which one is the largest capacitance. Remember, the reason why we look for the largest capacitance is that it's the highest, the largest bucket, meaning that it's the slowest node. So it actually determine the speed by the highest capacitance. In this case, the highest capacitance is CGS. CGS, we already derived that the 2/3 WL is supposed to be effective because this is the channel contribution from the channel. This is the area of the capacitance, and unit area of capacitance is Cox. Okay? Plus, so if I give you that number, you should be able to calculate. If I draw a particular size of transistor, you should be able to find out what CGS is. It's typically in the order of femto, maybe 100 few femtofarad, depending on the size of a transistor, of course, but you need to know the order of magnitude of your capacitance, especially parasitic capacitance, is typically less than a 1 picofarad. And plus an overlap, I have this overlap region times Cox. There's a diffusion length part, okay? And for CGD, this will be only the overlap plus Cox. Sorry, I missed one. Area. So area is WLD. This is the area times unit area capacitance. Once again, area times that. Okay? And then I did not discuss the junction capacitance. Typically, what you will be given in most of the model is also junction like this. Unit area junction capacitance. Like 0 simply means that you assume the bias voltage is at 0. So your junction capacitance, of course, we're adding some biasing dependency, but what happened is that you can determine your junction capacitance, CSB. It will also be determined by the area. Area is determined by W LS times CJ. And of course, CJ is a function of S to body potential. If your source and body is grounded, that will be, you simply use CJ0. And dB will be the same. It will be the area of your diffusion area times your junction capacitance, and it's also a function of drain to body bias. The highest you can go is CJ0, because it drops as you increase the potential, the bias. The more depletion, the capacitance becomes smaller. So the highest you can get is CJ0 at this parameter. Okay, as I said, for these parameters, you can only get a precise number once I have a layout. So that's what we typically do is called post-simulation. So once you have your layout, then you can determine what are these parasitic components are. And it will give you a more precise simulation results. Okay? So then we have already discussed this. I'm just going to quickly go through that. So when we do short circuit current gain of a MOSFET, it is frequency and short circuit current gain of a MOSFET. Is what we get is that you actually see a pole at 0 frequency. Therefore, there's a drop of minus 20 dB per decade. And the key important thing is the intersecting point of the short circuit current gain of a MOSFET. So this is omega t. So we already obtained that omega t is approximately your own transconductance and driving your own parasitic. So it's sort of like you're driving your own baggages. There's two, CGS, CGD. That's the main thing, main transistor capacitance which we're driving. These are not actually critical in most of the, when we discuss short circuit current gain. Okay? So we already derived that. So the next thing we're going to talk about is what are the key parameters that determined this frequency, the bandwidth, where I want to highlight again, this is 0 dB. So when does it intersect with 0 dB? That's the definition of transition frequency of a particular transistor. So let's write down what are the limitation on transit frequency. So the transit frequency of a MOSFET is determined by omega t, once again, GM, CGS, CGD. And we know that GM, you can write it down as mu at n channel. I'm using m channel device, W over L. I'm simply not going to differentiate L in detail. We're just going to assume that L equals to L effective. Here, we're just going to assume that lateral diffusion is much, much lower than L. That is to say that your L effective is approximately L. Whatever you draw is the actual distance between of your gate, between source and drain. So this is VGS minus VTH. So this is GM. And remember, in this case, we're going to assume that CGD is much, much smaller than CGS. If this is the case, then this can be approximated as mu n Cx W over L. Okay? Divided by this. And we're ignoring this overlapping capacitance, so this will be 2/3 mu n Cx. There's no mu, sorry. 2/3 W L Cx. Okay? The reason why we're doing this type of exercise is to let you know what are the things that can be done in order to push further on your bandwidth boundary. So you want to take out the parameter which is ineffective. For example, if I want to push for a wider bandwidth, meaning that I want to increase my transit frequency, you increase the channel doesn't help because your capacitance increase with the increase of GM. And also, by making your transistor with thinner gate dielectric doesn't help because it goes in the same direction. So what you're left with is this, mu n and there's this constant, it's not very effective. So once we see this equation, it's very obvious that one of the most effective way of pushing for wider bandwidth or faster circuits is simply which one is the most effective way. If you look at the equation, how do I push this to a wider, higher frequency? Give me one. Which one will you pick? What do you try to engineer? Correct. So if you want to do a faster, you want to make faster circuit, this is what happened while we're pushing for technology, you see technology 5 nanometer, 3 nanometer. The reason for that mainly is because this. This is actually the we call the conventionally, I want to say that. So this is called the feature size of a technology. What I meant by this is that if you ever heard of a semiconductor industry, they talked about technology going down to, for example, 5 nanometer, or if you look at the news, 1 nanometer technology. There's actually pushing for the minimum feature size, I should say, minimum feature size. We're pushing to make the smallest distance can be defined in integrated circuits. So you want to, which one you want to make it minimize? Of course, it's L. You want to make it as short as possible so that you gain the best in your circuit speed. So this would be faster circuit. To push for faster circuit, what you do, the most effective way is to do L. To make L as small as possible, that means that you need to go for smaller feature size. More advanced, I should say, advanced technologies. Okay? So let me give you some numbers. If you're using, for example, 0.18 micron, this is like the classic legacy process. Typically, your FT is around 50 gigahertz. So this will be very challenging if you're making circuits which operate in 5 gigahertz. It's about at the boundary, you want to have a marginal room between, as I said, you want to make your circuit maybe 10 times. So this might be your circuit operating frequency. So your circuit bandwidth must be slightly higher than omega t, because at omega t, you don't actually get any gain. So more comfortable, you need to have some margin. The margin is about 10 times or maybe 20 times. So if you have 50 gigahertz, you probably can only design circuits which operates at 5 gigahertz. So if you want to do 10 gigahertz circuit design, what do you need? You need to spend more money to go design or make your transistors, make your circuits in a more advanced technology. For example, so you want to push for, you ask your boss for more expensive resources. So for example, for 65 nanometer, you're expecting your FT should be approximately close to 200. This is based on this model. It will predict that your omega t can be pushed to 200. So you get more comfortable room in order to design faster circuits. But in real case, this is by that model. But unfortunately, in most cases, you actually only get a gain. This is about 3 times. Oh, yeah, that's about right. But I'm just saying that it will not get your square root response. In most cases, you probably get let me highlight. For shorter channel devices, your omega t will be proportional to L 1 over L instead of 1 over L squared, meaning that it will not get, if you look at this, you should get a 9 times increase, but in real case, you probably only get it 4 times. The main reason is because of this. For shorter channel, you get a frequency dependency less aggressively. This is because of some non-ideal effect. If you take courses in solid-state circuits, you get a sense as to what happened. These models will no longer hold in shorter channel devices. Okay, so aside from L, what else can we do? If you look at the equation, what else can we do? You make it smaller, and then you push for what? This one, even though it's right here, it doesn't actually help too much because this depends on your supply voltage. It's typically limited by, if you actually do design, you know that this is, the maximum you can go is VDD. So this is typically limited by this. So VDD is the supply voltage, and typically it would actually go down with scaling technology. So there's very little we can do. In terms of technology, what the next best thing to do is to change this. So as I said, you do something called a strength technology. And this is very common in nanometer technology. You will see that you probably, this is like, as I said, you twist your crystal so that your carriers move faster. That's basically what it is. Okay? So this exercise is mainly to tell you that the main pushing force for scaling, technology scaling, is actually speed. You want to make your circuits run faster. The best thing to do is to scale, to make it smaller so that it has faster transistor, meaning that you have higher driving current and smaller capacitance. The smaller if you look at this, this is the increase your drivability is the top, on the numerator. In the denominator, this is reducing L will then lead to smaller capacitance. So smaller bucket, higher current, that will then allow your overall circuit performance to push for higher frequency or higher bandwidth. Okay, good. So the next thing we're going to do is that we're going to talk about, go back to circuit analysis and go back to think about how does one analyze a complete frequency response of a single stage circuit. So we're going to talk about frequency response. I'm going to limit most of my discussion on MOSFET since bipolar is not in the exam. So frequency response of a common source stage. Okay? So if I give you a circuit, something like this is the circuit we have already analyzed before. Now I'm just going to talk about, we're going to separate it into two regions. One is at low frequency. At low frequency is typically limited by external capacitance, and a high frequency is determined by parasitic capacitance. So we're going to start with, this is a source generation example. And then it's being biased, the circuit is being biased by a resistive network so that we can actually have a input resistance being set up. M1, RD. So this is once again, this is a simple common source stage with source generation circuit. So we want to analyze its overall frequency response. And I'm going to add two external capacitance. One we have already discussed is the coupling capacitance CI from the input terminal. And then I have my input signal. Use a different color. So this would be my Vin. And then the terminal at VL, at the drain. And then we're going to add another type of capacitance, which are also very common in this type of biasing circuit, is this. We haven't discussed the effect of this. It's called the bypass capacitance. So I have one CI as coupling, input coupling. is a coupling cap. And CB is called a bypass. Bypass cap. And we're going to explain why it's called a bypass cap. There's a particular reason why you want to add it. So first we're going to do the low frequency. We're going to separate, as I said, we're going to separate our frequency response characteristic like this. We're going to do the Bode plot of this complete circuit. Omega, this will be the gain as a function of frequency. And there will be a phase. We're going to do the plot right here. Okay? We're going to separate into two regimes. One is low frequency. And as I said, you also want to look at, this is the mid-band. We actually already know our mid-band response, but I'm just going to. And then you have these high frequency. Okay? So does anyone want to sort of guess what our mid-band response is? This circuit. Mid-band is when you don't see these. You actually see this, but we're going to talk about. This will be, at mid-band, this will be short, this will be short. External capacitance, and let me. Mid-band is when, write it on the right. For mid-band, the two assumption is that external capacitance, whatever you added, external cap, meaning CI, CB, view as short. Because frequency is high enough, your capacitance is short. Mid-band assumption, I should say mid-band assumption. External capacitance is short, and parasitic will have CGS, CGD, DB, SB, US. You ignore that as open. So you don't consider the high frequency. The small capacitance, we're not considering its effect at this mid-band. So what do you expect your mid-band gain to be? What do you think? Any thoughts? If you look at the circuit, this is short. Your input, this is short. So what is your gain? Common source. What is it? Any thoughts? 5 stickers? No one wants to help. Because it's different because this is short. So if this is open, you see degeneration. If this is short, then you don't see degeneration. So what is this gain? Correct. Very good, very good. So you actually, this is very good because you should supposed to get your mid-band results first. So we know that this, again, at this level, should be GMRD. The reason why you don't see RS is because it's short. So that is why it's called the bypass capacitance, because you want to bypass the effect of RS. Remember the reason why, when we discuss biasing circuit, the reason why we're adding RS is to set our DC level to be a stable level. You don't actually want the effect of degeneration. You only want it sort of your current can be, the DC current can be stabilized. So at DC, this is open, you actually see the effect of RS to set your DC current. But then you don't actually want it when your signal is coming through. So this is actually mid-band. And mid-band is an inverting amplifier so that your, let me get a color, good color. So it should be at, let me start at, Because this is an inverting amplifier, so it should be minus 180 or 180. This doesn't really matter. It's an inverting amplifier, a common source stage. Okay? So let's look at what happened at low frequency zone. There's 1, 2, 3 zones. So let's look at low frequency when we consider these capacitance. So the way to do this is, of course, we introduce an intermediate state. This is Vx. Okay? So then your Vx, we could, this can be lumped into a Thevenin equivalent circuit. So if you actually do that, your Thevenin equivalent circuit will be something like this. Your input terminal will be R1 in parallel R2. Your equivalent, the equivalent will be you're looking into an R1 equals to R2. So then Vx can be represented as R1 in parallel R2. R1 in parallel R2 plus j omega Ci. This is the same as a high-pass single time constant circuit. So we already know that by this circuit, it would then introduce, let me write it down, j omega Ci, R1 in parallel R2, 1 plus j omega Ci, R1 in parallel R2. So this simply means that I will have a omega z at 0, and I have a first pole. My first pole is at Ci. Okay? You saw with the rising, this is what happened in a coupling capacitance. So let's say if my omega p is right here. Let's say omega p1. So I'm expecting my gains to go like this. Characteristic at very low frequency should be a low pass. As it rises to this level, will turn in as flat. And then it's not actually connected to GMRD yet. Okay, let's try to find the second term. So for VL versus Vx, when this is considered, sorry, Vx over Vn. This is Vx over Vn. So if you do the second part, which is VL, Vx, this term will actually get something like this. Minus GM RD. Remember, this is a degenerated circuit, so what happened is that you have a gain of GMRD being degenerated by 1 plus GM. Instead of only having RS, you're having an impedance when you look down at the emitter. The effective impedance, looking down, will be RS in parallel j omega CB over 1. Okay? So you're simply going to use RS plus j omega CB over 1. Okay? So if you do some simplification, this can be rewritten. This equation can be rewritten as GMRD. The degenerated results, you actually reach a degenerated state when you don't see this. You see the degenerated effect. When frequency is not high enough, this is not comparable to RS, then you actually see the degenerated effect. But then there's two frequency components. Let me highlight, there's omega Z1. So we already have a 0 at 0 and a pole at this corner. And then the second term will then introduce another pole and 0. Yeah, let me write it down. It will introduce a omega Z2 and omega P2. So omega Z2 will be determined by RSCB over 1. Omega P2 will be RSCB 1 plus GM RS. Okay? So in this case, we already know that we have omega Z1, which is smaller than omega P1. And in this two term, I already know that this is larger than 1. Therefore, omega Z2 comes first, and omega P2. So first, you need to align your frequencies. We start with a 0, 0, and then a corner. You hit a pole first, and then you're supposed to hit another 0. So we're going to hit omega Z2. And then finally, you're going to hit omega P2. So Z2 will be determined by bypass capacitance and this source resistance, RS, source resistance. And then it will rise again. I'm going to ignore the 3 dB just to get the trend. Okay. And we know this level is when between omega P1 and omega Z2 is when this is viewed as open, this is viewed as short. So you get the degenerated results, meaning that this gain should be, this level should be GMRD 1 plus GM RS. Okay? So interestingly enough, we know that this is plus 20 dB, plus 20. So once again, you start with plus 20, you hit a pole, flatten, hit another 0, plus another 20, and then hit a pole to get a flat. Okay? And one of the things I would like to highlight is this. Color. You're supposed to get another same ratio between the two. 这个等腰三角形。所以 what it means is that based on this 20 dB per decade ratio, omega P2 over omega Z2 should equals to the height. So it's GM RD 1 plus, GMRD 1 plus GMRS. Therefore, it's 1 plus GMRS. Okay? So you see it's supposed to coincide with what we obtained up there. The ratio between the two should be the same as the ratio between the two. And it's 1 plus GMRS. Okay? So let's take a break for 10. We'll come back and do the summary on high frequency. So we're going to do this region. Wait. Let me continue our discussion. So we can take a break at 20 so you get 10 minutes to prepare. Okay? Good? So let's not take a break. Let's just finish our discussion. 你们想要 break 吗？还是想要 continue? Probably get a better story. So then So you get a flow. Do you get a flow? No. No one gets a flow. So then we look at the high frequency. Remember, at this low frequency, these characteristics are determined by Ci and Cb. Right? The turning points, all of them are determined by this external capacitance. And if you want to do the frequency domain, you start with the 0, so you start with the minus 20, minus 90. The reason for the minus is, of course, because it's a space of 180. So you got it minus 90. And then if I do the plot, it will look very weird. It will go down. And then when it hits the 0, it will come up. And then it will go down again. Once again, you start with 90, and you hit omega p1, drop another 90, comes out with a 0, and come down with a pole. Okay? So if you look at the high frequency part, we're going to use our high frequency model. So the circuit will look something like this. Your equivalent circuit, I'm thinking the input part, we're going to use Thevenin equivalent. So this will be R Thevenin. It's actually R1 in parallel R2 in this case. And then I have a Vn. Then it would then come in to the circuit like this. In this, when you consider high frequency, remember this is short, this is short. So your equivalent circuit would then have a source connected to ground. This is CGS, this is CGD. And then I have GM, VGS. And then we're going to ignore R out. This will simply be R load. RD, yeah. Okay? So if you want to analyze high frequency, this is for high frequency regime, what happened is that in most of the common source configuration or common emitter configuration, one of the problems is that you have CGD as the Miller capacitance, feed-forward. So this will then be amplified by Miller equivalent, Miller amplification effect. So then my equivalent model will then this will be CGS. This will be still GM VGS. RD. So my CGD would then be separated into equivalent capacitance C1 and C2. If you think about it this way. So then from input terminal, from, I should say, node 1, there's node 2. So from input terminal, my overall capacitance will be CGS plus C1, which is C output terminal. I will get CGD plus C2. Where C1, by Miller effect, is 1 plus GM RD over CGD. C2 will be 1 Okay? So this exercise just simply tell you that your input terminal will then have the lump sum of capacitance, highest capacitance because of two effects. One is CGS is actually the highest capacitance. The other is C1, which is the Miller being the V4 capacitance being amplified by Miller effect. And then you get the overall high capacitance from the input terminal. Okay? Let me revise this. This is another example. This should be in parallel. In this case, because we have a network like that. So let me not use this. R1 in parallel R2. Okay? So then I should be able to get my two poles. From this exercise, we already know that from node 1, from input node at high frequency regime, so this is our high frequency regime. What happened is node 1 will contribute a omega, we're already at omega P2. So this is omega P3, which will be determined by input terminal in parallel to C in over 1. So as I said, from the input terminal, you actually have CGS plus the amplified CGD. And from node 2, you actually have CP4. And it will be determined by RD and C2. I made a mistake. This should be just C2 itself. Plus, if you want to be more comprehensive, you should be able to add another junction capacitance, CDB. Your output terminal will see the loading or junction capacitance plus C2. So this will be RDC out. Okay? So because in most cases, C in will be higher than C out. So we expect that omega P3 will be smaller than omega P4. You will hit omega P3 because of Miller amplification effect. Okay? So if I want to complete the plot, I will then see two poles. One is right here, omega P3, and then I'll have omega P4. But these two will not be very further apart. The main reason is because your output terminal resistance RD is typically not very small. So that because of this would then lead to a higher output, also a lower frequency pole. So let's complete our plot. So then what happened is that would then drop at a rate of minus 20 dB per decade. And then once it hit another pole, it would then drop further down at a faster rate, 40 dB. Okay? And if you want to look at the phase, as I said, it will then be 180. And then once it hit another pole, it would drop a 90. And then drop another 90. So overall, it will be 0, 330. Okay? Do you get that? Let me just make sure that my scales are. Make sure that your scales are correct. I don't have enough space for that. Any questions? So this will be your complete. It will be more complicated with 0 because there's 2 zeros in the low frequency regime. And there's 2 poles in the high frequency regime. Okay? Good? So I think I'm going to stop here to give you more time to prepare, or you have any questions, please bring up and I could explain. So we might be able to move faster because I'm going to skip all the bipolar part. Okay. Once again, for those of you who's coming late, we're going to have a final exam in 2 weeks. Remember, there's also homework 4, which will be posted this week. I think probably today. And there was only 1 simulation question, just to get you familiar with simulation on high frequency response. And for final exam, it will cover chapters 6 to 11, except OP circuit, which is at chapter 9, I believe. And as I said, after aligning with Professor Huang, our questions will be limited to MOSFET device and circuits. So you can skip the bipolar if you really hate it. As a reference, it's good to know what actually happens in a bipolar circuits. Okay? Any questions or feedbacks on that? This is very important. Remember to come for exams. We'll actually held our exams in 2 rooms, right? This room and 202? 202. So make sure that you come in early to get the C assignment. We'll have seat assignments. So we'll be at 202. What is the number for this room? 216? 17? 17. There's 2 rooms. So come in for the seat assignments or assigned seats. We'll post these assignments beforehand, so just make sure that you come in earlier to get the right place. Okay? Questions? No? So let's, we're not going to start early just to let you get prepared. 有没有什么问题？讲中文也可以。我讲一下有关那个讲一下有关期末考的事情，好，用中文讲一次。就是期末考很重要，就是大家记得来考试。然后呢，我们还有最后一次作业，好，那作业你要记得交。就是如果我再提醒一下，就是如果你有任何觉得你可能会被当掉的危险，哈 ，make sure 你一定要把所有的作业都要交，小考都要考，哈，就是。这些东西都不能够有任何 miss 啊！如果有 miss， 我们就没办法救你哈。然后能够让你尽量期末考好一点。那我们期末考刚才有讲过，就是我们会 focus 在 MOSFET 的 device 跟 circuits， 好，所以后面讨论大家都可以，我尽量都会只会讲 MOS 的部分 ，OK？ 好，那大家就这样，有没有什么问题？大家没有很想念bipolar？好，那有什么问题也可以上来。